Hello, everyone. Welcome to today's plenary. Good to see everyone out there, although I can only virtually see you. I'm very happy today to introduce our invited plenary speaker, Professor Amir Ahmadi from Princeton, where he is a full professor in the Department of Operations Research and Financial Engineering at Princeton University. He's also an associated faculty member of the program in Applied and Computational Mathematics, the Department of Computer Science, Department of Electrical Engineering, and the Center for Statistics and Machine Learning at Princeton. Professor Ahmadi received his PhD in EECS from MIT and was a Goldstein Fellow at the IBM Watson Research Center prior to joining Princeton. His research interests are in optimization theory, computational aspects of dynamics and control, and algorithmics and complexity. He has a number of distinctions. I'm going to be brief here, but I'd like to mention he's received the Sloan Fellowship in Computer Science, the very prestigious Presidential Early Career Award for Scientists and Engineers, as well as the NSF Career Award, the DARPA Faculty Award, and the Google Faculty Award as well. Amir Ali's research has been recognized also by a number of Best Paper Awards, the Informs Optimization Society's Young Researcher Award, the Informs Computing Society Best Paper Award, and also a Best Conference Paper Award at IEEE International Conference on Robotics and Automation. I should also mention he's won several teaching awards at Princeton as well, so I'm sure we're in for a very nice talk. I'll mention very briefly that you could submit questions to the speaker through the Q&A feature of Zoom or through the chat, and I'll try to moderate those and get those to the speaker towards the end of the talk. He may also stop in the middle to answer questions as well. Today, Amir Ali is going to be speaking to us about the complexity of finding local minimizers of polynomials over polytopes, and then making some connections with stable sets and sums of squares polynomials. So Amir Ali, please take it over. And make sure to unmute yourself there.
Okay. Yeah, thank you, Sam, for the very generous introduction. Indeed, I'm going to talk about local minima, stable sets, and sums of squares. So my plan for today is to define, is to define the terms in the title, present one negative result, one positive result, and make one connection. So these will be the three main theorems in the talk, and when they show up, you'll see them with these icons and recognize them. Everything that I talk about is joint work with two very talented graduate students. One is Jeffrey Zhang, who graduated last year and is now at CMU in the math department. And one is Jamil Debek, who is graduating later this year. Okay, so I want to start very high level, and this is a picture that you would typically find on the cover of an optimization textbook. Some of you may recognize this as the book by one of the books by Jean-Bernard Lasserre. And the picture is very suggestive. You see a very complicated looking, non-convex looking function with lots of peaks and valleys. And in optimization, sort of our goal is to find a global minimum often, or that's like the primary goal. But as this picture sort of suggests, that may be a difficult thing to do because of all these different local minima that are out there. So you may think, at least if I run some sort of a local search algorithm starting from a particular point and do descent, hopefully my algorithm would end up at a local min that I can return. So for the first 2/3 of this talk, I want to study this question a little more formally. So if global minima are hard to reach, can we at least find a local minimum efficiently? When can we, and maybe when can we not in some settings? But as I was thinking about how can I present the typical behavior of algorithms on such problems without getting into the specifics of a particular algorithm and do it in an abstract way, I had the good fortune that I literally saw a little ant coming near the book by Lasserre, and I thought, okay, maybe it's good to start with a fun experiment and ask, can this ant find a local minimum of this polynomial, right? So we're going to think of the ant as a hypothetical abstract algorithm. And, I was worried about that the ant may not remember the definition of local and global minima. So I'm giving it very precise instructions. I'm asking it, please go here, but if you can't, at least go here where there is a local minimum. And it's sort of interesting to see what the ant does. Is interesting to look at the trajectories and think of like reverse engineering what algorithm is running. And this is one typical behavior. And of course, this is a joke, but I don't know what this looks like to you, but to me, it looks like the stochastic gradient descent, sometimes with some acceleration and momentum. In this case, the ant just goes off to the left. But if you keep doing this, you see very familiar behavior. So if you just gently press the ant in the head for a few seconds and then leave it close to a saddle point, you see that the ant struggles to move because the gradient is too small and it takes very small step sizes. Luckily, with a random initial perturbation, it finally gets out of the saddle point. You keep doing this for a while and the ant fails to find the local min. So you think of a technique that we always use in optimization. What if we force the ant to start near a local min? So think of a smart initialization. It turns out ants don't really like this, and this really backfires. So if you see what's going to happen, I place it very close to the local min and the algorithm very quickly diverges. You can play this game for a while, and I spent about an hour with this ant and with all sorts of imitation learning or reinforcement learning techniques and giving the ant proper punishment and reward. Finally, the ant manages to find the local min, as you'll see here in this video. And it stays there for a while here. But now, all joking aside, the question I want to a little more seriously answer is, let's forget about this ant. Let's think of all ants in the world or all algorithms. Maybe this ant wasn't the brightest one. How fast can the best ant or the brightest ant or the best algorithm find the local min? And how do we formalize this question? And there are different ways of formalizing it, but I want to talk about a particular setting. So before I do that, let me also formally define what is a local minimum. And now I'm going to get to the more serious part of the talk and switch to my laser pointer. So here I'm defining it also in the setting where you have a constraint set omega. And as we all know, a point is a local minimum. Well, if it's first feasible, and if there exists a neighborhood of some radius delta, such that if over that neighborhood you compare the objective value of at x bar to the objective value at any other point in the neighborhood, which is also feasible, then x bar is better, or at least is no worse. So in this one-dimensional example here are 3 local minima of f over the set omega. Okay, now the question of how fast can you find local minima, of course, depends on what f and omega are and how they're represented and how they're given to you, right? So I claim that it's very insightful to focus on the case where the data to the optimization problem is given by polynomials. So the objective is a polynomial function, and the feasible set is defined by finitely many polynomial inequalities. So why is that? So first of all, this already covers the most common optimization problems that they face in the literature of optimization, both in practice and theory. Second, because local minima are a local notion, and polynomials are a good test case because they can approximate more complicated functions locally, as is well known. And finally, because polynomials are finitely parameterized, this allows us to very rigorously study this question in the Turing model of computation. So we can take the input to the problem to be all the coefficients in all the polynomials that appear in the problem, take them to be rational numbers, count how many bits it takes to write down these rational numbers, and that would be the size of the input. And then we can ask, how would the best algorithm scale as a function of the size of the input? How fast can it run? And typically we'll have the degree d to be fixed, and we let the number of variables in the problem grow. So that's the setting. So let's think about the smallest, the first simplest case to consider. So that would be the case where omega is polyhedral. So all these functions are affine. And f is also a linear function. So that's, of course, linear programming. We know in that case, local minima are the same as global minima. Then they can be found in polytime. This is all classical. Now, what is the next case? Well, the next case would be if I keep omega polyhedral. So I'm going to keep all these GI functions to be affine. But now I increase the degree of f, the objective, by 1. F is quadratic. So this is what's called quadratic programming. Quadratic function over a polytope, right? And it is well known that global minima now become NP hard to find. And the question is, can we at least find the local minima, right? And we're not the first to ask this question. In fact, this question was very explicitly stated in '92. There's this nice short paper by Pardalos and Vavasis, which at the time they proposed 7 open problems for complexity theory numerical optimization. Some of them by now are solved and some are open. And this is question number 3. And it's very explicit. It says, what is the complexity of finding even a local minimizer of a non-convex quadratic program, assuming that the feasible set is compact? Okay, and then they go on to explain that there's a related result by Murthy Ahmadi and Pardalos and Schnittger that says, if you have a quadratic program and if I hand you a point, sometimes it's hard to certify that this point is a local min, but that does not rule out the possibility that maybe there's another local min that an algorithm can easily find and recognize. Right. So I want to make 2 remarks about the statement and why they're asking the feasible set to be compact. Well, that's because if the feasible set is compact and the objective is quadratic, then by Weierstrass's theorem, we know that there is going to for sure be a local min, right? Because there is a global min in particular that's at least one local min. So this is a setting where the existence of what we're after is guaranteed, and the question is just about finding it. So if you wish, is similar to the setting where you ask to find the Nash equilibrium in a game. So there's not a decision question. The existence is guaranteed. Is about the search. And second, it was already shown by Vavasis in a nice paper that shows quadratic program is in NP, that there is always a local min, in particular a global min, that has rational entries, and the rational entries are not too large. They have polynomial bit size. So this is also nice because it says that if I have a QP, then there's definitely going to be a nice local min with small bit size. The only question is, can I actually find it, right? And this is the first result of this talk, is the negative result. So with Jeff Zhang. So what we show is that unless P equals MP, there cannot be a polytime algorithm that does this. And the result is actually a bit stronger. It shows that not only you can't find local minima, you cannot even get close to them. So you cannot find a point which is within distance C to the N of a local min, where C is any constant. So you can fix it to be 2 or 1,000 or anything you want. Right. So I hope the statement is clear. So the proof of this goes through the second phrase in the title of my talk, which is about stable sets. So let's forget continuous optimization and talk about a basic notion in combinatorial optimization. So what's a stable set in a graph? Is a set of vertices that are pairwise non-adjacent. So for instance, the 5 red nodes in the graph, they don't share any edges. So if you pick any of them, 9 and 7, for instance, there is no edge. So this is a stable set of size 5 because there are 5 nodes. And the size of the largest stable set in a graph is called the stability number of the graph, and it's denoted by alpha of G. So in this graph, alpha of G is at least 5, as you see, and is sort of not too difficult to show that there is no stable set of size 6. So indeed is alpha of G is 5. And one of the most classical NP hard problems in the literature is exactly if I give you a graph G and an integer R, which is between 1 and n, because alpha is always between 1 and n, can you tell me if alpha of G is more than or equal to R? A different way of saying it is, can you tell me if the graph has at least one stable set of size R, right? And this was shown to be NPR by Karp. So what we show here is that if you had an algorithm that could get within distance C to the N of any of the local minima of the quadratic program you see here, this algorithm would allow you to solve the stable set problem in polytime. And of course, that would imply P equals MP, right? So what is this, this construction in this reduction? So what you carry over from the first decision problem is that the integer R and the adjacency matrix A of the graph G. Everything else is fixed. So I is the identity matrix, J is the matrix of all ones. And the constraints are non-negativity constraints plus one more, which makes the feasible set compact as requested by Pardalos and Vavasis. And this number here, we're taking the ceiling of it, so it's an integer. Now you may worry for a second if this is a polytime reduction because there is C to the N here, but you should be reminded that the number of bits you need to write down C to the N is N. And that's definitely okay because you need order n square bits just to write down the matrix A. So this is indeed a polytime reduction. If you don't like C to the N, you can also replace this whole expression by N and you get a similar result with a slightly worse quality of approximation. Okay, so I won't be able to prove why this works, but I can just give you sort of the structure or the outline of the proof at a super high level. So what we show that if you look at this very specific quadratic program, then the following is true. If the graph that you started with, if all of its stable sets are strictly smaller than R, then this quadratic program is going to have a unique local minimum, which is at the origin. So remember, there's always going to be a local min somewhere in this orange triangle. We just don't know where it is. And in this case, it will be at the origin and it will be unique. Now, in the other case, if there is a stable set of size at at least R, then there could be many local minima, but all of them would be on this edge. In other words, for all of them, this last constraint would be tight. Okay, so this is where the work goes. But of course, once you have this, the rest of the proof is simple, because suppose there was a polytime algorithm that, given a quadratic program, always landed within distance c to the n of one of its local minima. Well, then run that algorithm on this particular QP, right? So you can see that the distance from the origin to this hyperplane, you can calculate it to be 3 times c to the n. So these are points in blue that are within distance c to the n of the origin. The points in this orange band are points that are within distance c to the n of this hyperplane. So if algorithm comes with this guarantee of always being within distance c to the n of some local min, the algorithm will never land in the white area in the middle, so that's no man's land. It will sometimes go here and sometimes go there. Well, if it goes to the blue, you know that the local min must have been at the origin, and you can conclude that alpha was less than R. If it goes to the orange, you know the local min must have been somewhere on this hyperplane, and therefore alpha is more than or equal to R. You've solved the stable set problem, which implies P equals NP. So that's sort of the high level outline of the proof. So before I move on, I want to make one remark, at a sort of a slightly more philosophical remark, because I've noticed that some people in our community sometimes tend to think that, oh, if a problem is NP hard, maybe it's just there's some occasional hard instances that we can't solve, but it can be okay most of the time and sometimes we have over expectations from our heuristic algorithms. And this is not the case. So it follows from some results in complexity theory that, let me just say it specifically to this problem, that if you pick your favorite polytime algorithm for finding a local min of a quadratic program. So let's just have an algorithm in mind for concreteness. Maybe it's gradient descent with a particular step size and with projection back to this polytope. Let's just fix that, right? And you may wonder, if I run this algorithm on QPs, what would it do? And if we think of all QPs whose input data can be encoded with k bits, there's 2 to the k of them, your algorithm is guaranteed to fail, meaning that it would land far away, exponentially far away from any local minima on a large number of instances, in particular on a number of instances that cannot be bounded by any polynomial in k. So another way of saying this is that the number of cases where your algorithm fails or lands far from a local minima is super polynomial. Okay, so indeed, I think this type of results, they do have some relevance. Okay, so I'm actually good with time. So I'm going to move on to the case where I want to ask the question, what about the unconstrained case? So maybe this difficulty of finding a local min came from the fact that, even though my objective was simple and quadratic, I had constraints, even though they were polyhedral, which are sort of the simplest constraints you can think of. But what if I remove constraints? So the question now is, if I give you a polynomial of degree d, can you test if it has a local min? And if so, can you find one, right? And again, I want to emphasize this is different from the recognition question, which says, if I give you a polynomial and a point, can you test if this point is a local min? Here, I just give you the problem data and I ask you to find the local min. So it turns out that if the degree is at least 4, this problem is NP hard, and the same proof roughly that we gave on the previous slide can be massaged to also prove this result. I'm not going to get into that. Now, if the degree is 2, this is a classical situation, which is easy. Then for quadratic polynomials, unconstrained local minima are characterized by first and second order necessary conditions for optimality. At the first order, which is set the gradient equal to 0, gives you a system of linear equations. And the second order condition asks you to check whether a fixed matrix is positive semidefinite. You can do this in polytime. Okay, so that remains one case which is the case of degree 3 or cubic polynomials, which was interestingly missing from the literature. And it turns out that cubics are actually really interesting. They have some amazing both geometric and algebraic properties. In fact, this was noticed already 1,000 years ago, where Omar Khayyam classified, let me just turn my email off, the cubic polynomials in one variable. So of course, here we're dealing with multivariate polynomials, and we're interested in their local minima. And what I want to just tell you some intuition is that this is significantly more complicated than the quadratic case. Well, for one thing, because first and second order conditions no longer characterize local minima as one would expect. Another reason is that lack of a descent direction does not imply local minimality. So what do I mean by this? So here's an example of a cubic polynomial. I'm plotting its level sets in x1, x2 plane. And these are the places where the function is positive, and these are where it is negative. And of course, the cubic vanishes at the origin. Now, if you start at the origin and if you move in any line in any direction you want, you can see that you will locally increase the function. So this may fool you into believing that this cubic has a local min at the origin, but that's not the case, because if you move along this parabola instead in red, then you will immediately decrease the function, so which rules out the fact that this 0 is a local min. Okay, so the way we're going to answer this, so we're interested in the following question. If you give me a cubic polynomial, can I test if it has a local, can I find this local min? So how would one go about this? So if you think about how we teach our students in our undergraduate optimization class to find local minima, well, we tell them first find critical points, right? First set the gradient to 0, list your critical points, and then after that, you examine the Hessian matrix on these critical points, see when the Hessian is PSD, and from there you can filter this out more and eventually isolate your local minimum, right? So it's normal to ask, okay, can we at least find critical points? In fact, this is not the case. So we show that testing if a cubic polynomial has a critical point is also NP-hard, right? But somehow, surprisingly, or at least in sharp contrast to this, we can find local minima. So this is the second theorem of the talk, the positive result, which says a local minimum of a cubic polynomial can be found by solving a few number of semi-definite programs of size linear in the number of variables. So roughly, the message is you can find local minima of cubic polynomials by solving small semi-definite programs of linear size. Okay, so in other words, the right thing to do is not to first find critical points, because that's actually more intractable, and that is intractable. And the right thing to do is to directly go for local minima and combine first order conditions and higher order conditions. So I will not be able to prove this, but I will try to give as much intuition about the elements of the proof over the next few slides. In particular, I want to start with some geometry and a very clean and nice geometric fact about local minima of cubic polynomials, which is the following. If you have any cubic polynomial, if you look at the set of its local minima, this forms a convex set. Okay? So the statement is very specific to cubics, is clearly false for quartics, right? This is a quartic in dimension 1. It has 2 isolated local minima, clearly not a convex set. Right? And let's build some intuition over an example, a 2D example. So here's a cubic polynomial. Again, I'm plotting some of its level sets. And this is the set of its critical points, is the union of these 2 lines, is not a convex set, because it's sort of solution to some quadratic equations with some gradient structure. However, if I look at what are all the points where the Hessian is positive semi-definite, right? This alone is always a convex set, because the Hessian of a cubic polynomial is affine. So the entries of the Hessian are affine. So the region where the matrix is PSD is defined by a linear matrix inequality. So this region is always convex. So the intersection of first and second order necessary condition points are this red line, only this one. Not all of them may be local minima. In this case, it turns out that they're all local minima, and the theorem checks out. This is your convex set, this line. Okay. The way we prove the theorem on top goes through a characterization of local minima, where we figure out the right condition. So it says that a point is a local min if and only if it satisfies the familiar first and second order conditions. But there is a third condition you need to add, which is the following. So if you have any vector which is in the null space of the Hessian matrix evaluated at your point Z that you're examining, then the gradient of the homogeneous component of the top homogeneous component of your polynomial should vanish. So what is P3? So the polynomial itself is called P, and P3 is simply the collection of all of its terms that have degree exactly 3. So P3 is a homogeneous polynomial of degree 3. Take that polynomial, take its gradient, now you get a vector. Now, if you plug into that vector of polynomials any vector d, which is in the null space of the Hessian at z, this vector should vanish. That's the condition. We call it the third order condition. Sort of not hard to see that if a necessary condition would be that if d is in the null space, then P3 itself should vanish, because otherwise you will always have a descent direction. But you need a stronger condition. You need this gradient to also vanish to rule out descent parabola. That's sort of the intuition. Okay, and then this characterization, first of all, it gives a polytime algorithm for recognizing local minima. So if you give me a point, I can check these conditions in polytime. It doesn't necessarily tell you how would you find a point that satisfies this condition. So that's a harder question that remains for the next slides. But anyway, this theorem is also proved to is also used to prove this geometric statement on top, that the set of local minima is a convex set. Okay, so every time you have a set that you've proven to be convex, a very good question to ask next is it polyhedral? Now, unfortunately, this is not the case for cubic polynomials. Let me see why this stopped. But sort of the next best thing is true. The set of local minima of any cubic polynomial is semi-definite representable. So you can actually optimize over it with semi-definite programming. So this is sort of behind the theorem that gives the algorithm. Now, it's interesting that a converse is also true, and I'm going to be slightly imprecise about this here, but the details are in this archive paper. If you have the feasible set of any semi-definite program, this set can be written as a projection of the set of local minima of some cubic polynomial, right? And the construction of this cubic polynomial is very explicit in the paper from the description of the spectrohedron that you started from. And also this represents the first theorem, the set of local minima is semi-definite representable. This is also explicit, and this STP doesn't have large size, okay? A corollary of the second theorem is that if you had any algorithm for finding local minima of cubic polynomials, maybe again, some sort of gradient descent with some step size mechanism or whatever, this algorithm could be turned into a semi-definite programming solver. So an informal statement to remember from this slide is that roughly complexity of semi-definite programming is equal to the complexity of local minima of cubic polynomials. Okay, so what the only thing I want to demystify is, where does semi-definite programming come into the picture through all of this facts about cubic polynomials and their geometry? And the connection comes from sums of squares, as is probably unexpected for those of you who work in this area. So probably not unexpected for those who work in this area. And the connection really goes through this theorem, which says, let me see if I can remove this. There's something on my screen. Let me just ignore it. It says, if you have a cubic polynomial which has a local min, then if you want to see what is his local minima, or more precisely, the closure of the set of his local minima is equal to the solution set of the following optimization problem, or the set of optimal solutions to this problem. So in this problem, I'm minimizing the cubic polynomial that I'm given over the set of points where the Hessian is PSD. So we call these points, this set, the convexity region of P, because these are the points where the Hessian is PSD. So in this toy univariate example, this would be this yellowish region. This is where the curvature of the polynomial is positive. Now, if I minimize P globally, of course, I get minus infinity. But if I minimize it over the convexity region, I get this point, which indeed is a local min. And the theorem checks out in this simple example, right? Now, once we have this, the question is, how would you solve this problem? And essentially, we look at the dual problem or an algebraic dual problem, where the goal of this problem is to certify a lower bound on the optimal value of this primal problem. This lower bound is going to be called gamma. Gamma is a scalar. And the dual problem is looking for some function here, which is a polynomial, which is a sum of squares. So I'll get into this in more detail in the next slides, but this sum of squares polynomial is simply a polynomial that can be written as a sum of squares of other polynomials. And is also looking for a matrix of polynomials, which can be factored as RR transpose, such that this algebraic identity is true. So why is this interesting? Because now if I pick any vector x, which is primal feasible, and I plug it into this expression here, well, sigma of x will be non-negative because sums of squares are non-negative. S will be a PSD matrix because of this factorization. The Hessian is PSD because x is primal feasible. The trace of the product of two PSD matrices will be non-negative. And that shows that, okay, the primal objective is more than gamma, okay? So I just argued weak duality for you. What we show in the paper is that strong duality also holds at very low degree. So you can cap the degree of sigma to be a degree 2 polynomial and the degree of S to be a degree 2 matrix, and the lower bound that you get is actually tight, so there will be equality here at optimality. Now, as is well known, the search over sum of squares polynomials and matrices can be carried with semi-definite programming, and that's where the connection to semi-definite programming comes from. Okay. Okay, I have about 10 minutes, I think. So I think that's actually perfect for the last part of my talk. Before I move on, for those who are interested, I just want to tell you that what I presented is 2 cases from a more complete story. And if you're interested, I recommend that you look at Jeff Zhang's PhD thesis. In it, he completely classifies the complexity of not just finding local minima or recognizing them, but also for other notions of critical points, second order points, and strict local minima as a function of the degree of the polynomial. And as you can see, for all of these notions, for cubics, the problem is tractable, except the question of finding a critical point of a cubic. Okay. Now, in the last 10 minutes that I have left, I want to connect this notion of sum of squares polynomials, which we just saw, with the notion in graph theory called perfect graphs, which are very much related to stable sets, which I presented earlier. Now, the topic on the left is of classically a topic from algebraic geometry, which recently has seen a lot of connections to optimization through its connection to semi-definite programming. The topic on the right is in discrete math and graph theory, but also relevant to optimization, as I will explain. So I'll spend maybe 1 or 2 slides telling you, defining these things formally, giving you the context, and then giving you a theorem that connects them. So let's start with sum of squares polynomials. So a polynomial P is non-negative if it only takes non-negative values for any vector X that you plug into it. It's unfortunately not easy to recognize non-negative polynomials. So if I give you this polynomial and ask you, is it non-negative? Good luck with that. It seems pretty non-trivial to test that. But suppose I told you that you can take the same polynomial and rewrite it as a sum of squares. So if you expand the squares, you get P back, which is something you can easily check. Now, as soon as I give you this algebraic proof, you're immediately convinced that P is non-negative. So this motivates the definition. We say a polynomial is a sum of squares or SOS if it can be written as a sum of squares of some polynomials. I don't care how many, just some polynomials. And clearly, if you're sum of squares, you are non-negative. So there are 2 questions here. One is it any easier to test for a sum of squares decomposition? And this is well known, and I'm not going to go into it. And this is the reason this area of sum of squares optimization exploded, thanks to works by a lot of people. Some of them I've listed here. And then the second question is, well, is every non-negative polynomial a sum of squares? Now, in fact, this is an old question that was studied over a century ago by Hilbert. He showed in 1888 that when the degree is at least 4, there must be some non-negative polynomials out there that are not sums of squares. Interestingly, his proof was non-constructive, and he didn't give an example. And even more interestingly, it took almost 80 years for an example to be constructed. So this is the famous Motzkin polynomial. It has degree 6, and I can plot it because it has 2 variables. And then it took another few years for Robinson to construct an example of degree 4, and this is minimal in the degree. You cannot do lower than 4. What we know more recently, thanks to Greg Bleckerman, is that if the degree is 4 or larger, as the number of variables grows, in fact, these examples become very common. There are significantly more non-negative polynomials that are compared to sums of squares. However, in sort of dimensions we can handle with semi-definite programming, these polynomials are still extremely hard to come by and sometimes non-trivial to construct. In fact, we did not have an example like this, which was a convex polynomial. So the question of finding a convex non-negative polynomial, which is not SOS, was open until a couple of years ago and a couple of months ago. And this is something that I myself worked on for many years. And James Sanderson has resolved it. And there's a talk at 5 p.m. today. If you're interested to see that polynomial for the first time, I recommend you go there. Okay, so this is a bit on the story of SOS. Now, what are perfect graphs? So let me tell you first quickly what is a clique in a graph. So a clique in a graph is a set of pairwise adjacent vertices. So it's exactly the kind of the complement notion of a stable set. Remember, a stable set was a set of pairwise non-adjacent vertices. So cliques are stable sets in the complement graph. So for instance, in this graph, this edge, these 2 nodes form a clique of size 2. This triangle is a clique of size 3, right? And the clique number, which is denoted by omega, is the size of the largest clique in a graph. Now, there is a second interesting number, which is called the chromatic number of a graph, or the coloring number. This is the minimum number of colors you need to label the vertices such that no 2 adjacent vertices get the same color, right? So in this case, I've colored these vertices correctly with 3 colors, so the coloring number is 3. Now, it should be pretty clear that if I have a clique in a graph of any size, let's say of size 3, then I need at least 3 colors just to color this triangle, right? So a lower bound on the coloring number is a clique number. This is pretty obvious. Now, a graph is perfect if equality holds, if the omega is the same as chi. So the only reason you cannot color the graph with few colors is that there are some large cliques. That's sort of the intuition behind perfect graphs. In fact, the definition requires this to hold for every induced subgraph of G. So an induced subgraph means if you remove a node from the graph, any nodes that you want, and you also remove the edges that were attached to these nodes, you remain with a smaller graph, and that's called an induced subgraph. And the same condition that the clique number is equal to the coloring number should hold for that graph. Now, perfect graphs have a beautiful theory. They connect to integer programming. Many problems that are NP hard on general graphs are polytime solvable on perfect graphs. And perhaps the most well-known theorem on perfect graphs is this beautiful result that came in 2002, is known as the strong perfect graph theorem. It was conjectured in the 1960s and proven in this paper, which is about 150 pages long. It says a graph is perfect if and only if it does not have odd holes or anti-holes. So an odd hole, an odd hole is simply like an induced cycle of length 5, at least 5. So it should not have this graph anywhere in it. It should not have C7, C9, or the complement of any of these. Okay, so these are perfect graphs. So now, what's the connection? So I'm going to go a little quicker here to take a couple questions at the end. So for any graph G on n vertices and clique number omega, so omega is the size of the largest clique, we define a degree 4 homogeneous polynomial, which you can explicitly write down based on the H set of G. We call this PG. It turns out you can show that this polynomial is always non-negative. That follows from a theorem of Motzkin and Strauss with some work. And we say a polynomial is a graph is SOS perfect if you write down this polynomial for any of its induced subgraphs. This polynomial is SOS. Again, this PH will always be non-negative by construction, but if it's also SOS for every induced subgraph, we say the graph G is SOS perfect. That's a new piece of terminology. Now, here's the theorem. You probably guessed it. A graph is perfect if and only if it is SOS perfect. So if you want, you can think of this as an algebraic characterization of perfect graphs, and I won't be talking about the proof of this here. I just want to give you a quick example. So this is concrete. So if this is your graph, you can go and write down the polynomial associated with it. This polynomial is always going to be non-negative, but in this case is a sum of squares. And if you now look at the subgraph, induced subgraphs of G, you can also write down their polynomials. I haven't written that on the slide, and they're all SOS. So therefore, this graph is SOS-perfect, right? So what are some implications of this? So we've shown that the graph is perfect if and only if it is SOS-perfect. So what does this mean? That means that if you have any non-perfect graph, then there must be at least one non-negative polynomial hidden in it, which is not a sum of squares, right? But we understand very well what are not perfect graphs thanks to the strong perfect graph theorem. These are graphs that have odd holes and odd antiholes. So it turns out if you start with odd holes and odd antiholes, so these are the first two odd holes and the first two odd antiholes, you can write down these polynomials associated with them, and they would be non-negative but not a sum of squares. And then there's certain operations you can do to them to keep this property of not being a sum of squares. So here, all these graphs I'm showing, the polynomial behind them is non-negative, but not a sum of squares. So you can recognize these as Paley graphs, maybe some of you. Okay, so in this sense, this is nice because this graph theoretic notion is bringing something to the SOS community that it enables us to create non-negative polynomials that are not SOS and sort of understand what's the reason behind it. And in fact, if you try this construction on a random graph, random Erdős-Rényi graph with parameter p on n nodes, as n grows with overwhelming probability, this very concrete polynomial is going to be non-negative but not SOS. So you can think of this roughly as a discrete confirmation of the theorem of Bleckermann that I presented. And this checks out in experiments. So if I generate random graphs of size on 100 nodes or so, in every single case, the polynomial you get is non-negative, but not a sum of squares. So I want to end the talk with a challenge for the SOS community or the STP community. And like any good modern challenges should come with a hashtag. That's the hashtag. And the question is, can we now contribute something with our algebraic techniques back to the graph theory community? And perhaps the nicest thing to do would be to prove the strong perfect graph theorem algebraically. So remember, this is a theorem which says the graph is perfect if and only if it has no odd holes and no antiholes. And the very concrete algebraic reformulation of it would be the following. So if you start with any graph which doesn't have the cycles of like 5 or larger or their complements, then if you write down this polynomial, which is by construction non-negative, it will also be a sum of squares, right? If you can prove this, and if you can hopefully prove it in less than 150 pages, hopefully significantly less using techniques in algebraic geometry, convex duality, semi-definite programming, I think that would be a fantastic achievement. So I want to leave a couple minutes for questions, but hopefully this last part has made you interested to know a little bit more about sum of squares, which is really a beautiful topic when I only covered one small facet of it very superficially. Luckily, there is another plenary talk exactly in an hour by Didier Henrion, which also goes through sum of squares. And these are some textbooks and survey papers on the topic. If you want to know more about the content that I talked about, you can check the websites of myself or my co-authors. Thank you so much.
Thank you. That was really terrific. A lot of neat intuition and neat connections. Thank you so much. I think we've got time for one question. If anyone would like to put it in the chat or in the
I cannot see the chat, so if you could read it off, that would be great.
Will do. I'll give
oh, somebody asked what P3 was, John Dushi. Hi, John. Yeah, it's the top homogeneous component of P. Yeah, so Sam already answered it. Yeah. Yeah. It's too bad I don't see who's attending, so no idea what's going on.
It looks like we have about 100 or so participants if you click on the participant tab. I don't know if everyone can see that, but
yeah.
All right, just one more moment to see if any. Oh, looks like we have one question here. Yeah, this comes from Greg Bleckerman. Do you know what happened?
It's a great question. Yeah, I got it. Yeah, and I knew Greg would ask that. So that's interesting because
Amir Ali, could you read the question?
I'll repeat the question. Yeah. So let me find a way to go back. So the only algebraic way to show a polynomial is non-negative is not to show whether it's a sum of squares of polynomials. You can also show if it's a sum of squares of rational functions with some degree of the denominator, right? And so that would be a more powerful SOS proof. And what I think should be true, that as you have cycles of higher and higher length, the degree of this denominator should go up. Now, exactly, I don't know the dependence. I would guess that they should go up at least linearly. But this also actually can introduce another notion, like you can define a two perfect graph, which is the set of graphs where for this polynomial is one SOS, right? Meaning that it has a denominator of degree 2. And it'd be interesting to know what that means graph theoretically. Now, can you classify the graphs to go the other way, that whose polynomials have a certain type of SOS proof of some degree? So yeah, Greg, that's a great question. I've thought about it and we know very little about it. So hopefully more connections will come.